Amy and Najib, welcome to today's class. Today we are going to talk about limits. Limits is a very important concept, and as I've seen in your curriculum, in both Amy, your curriculum, and even in Najib's curriculum, limit is not a part of calculus. But anyway, we don't want to skip it. I will only take 3 classes to complete the whole concept of limits. We actually began with limits to, if you remember, we calculated the value of E, right, with the limits, correct,
Right.
of a particular function. So calculus cannot be done without limits, right? So it's kind of important. So I'll take 3 lessons. In the first lesson, I'll give you concepts about limits. In the second lesson, we'll talk about the indeterminate form and how to, find limit for complicated functions. And the third lesson will be exam review. Today's lesson is more interactive. I've built up this concept of limits so that you can actually understand and answer the questions straight on. So I've kept it very interactive. I would like both of you to just speak out the answers as we read the questions. Faster it is, better for us, since we have only 30 minutes to go, right? So a lot of things to pack up in 30 minutes. Let's share the screen. And here is the screen for us. Can you see the screen?
Yes.
Both of you.
Yeah.
Okay, so be prompt today and be loud. So we'll talk about the limits of the function, lesson 1, basic concept. The very first sentence which I've written, equation is a sentence you know. Limit sine x over x when x approaches 0 is equal to 1. Now, you know that sine x for x equals to 0 is 0, right? X for 0 is also 0. So we have a form here which is kind of 0 over 0. And we are saying 0 over 0 is equal to 1. Is that what we are saying? Not really.
No.
We are saying limit of this particular function when x approaches 0 is 1. So limit basically is not at that point. It is very, very close, arbitrarily close, extremely close, but not at that point. So we are approaching 0. And when we approach 0, we approach 0 from both the sides, all directions. But we are just approaching that value. And when we approach x equals to 0, we find that the expression sine x over x is equal to 1. The graph on the right side, which you see, clearly shows that as x is approaching 1, x is approaching 0, sine x over x is approaching a value of 1. Correct? So that is what the beginning is. And the last statement on all the topics which we are going to cover is next topic, indeterminate forms. Now, indeterminate forms are the forms which are 0 over 0 types or infinity over infinity types. So those are the expressions which you cannot evaluate. But with the help of limits, we can have an idea of those expressions when they're approaching a particular value. And that makes things very good for us, right? So we can now analyze the functions which were thought to be indeterminate. So that's the whole idea. So that's the power of limits. So we'll begin with the concept of limits. We'll evaluate limit for the graph, limit, and we'll see how to find the limit from the left side and the right side. Since I mentioned that you have to approach from both the sides. The two sides in 2 dimensions will be left and the right. We'll see the continuity of the function. We'll also check into discontinuity. We'll work on piecewise functions. And then we actually began with indeterminate form. We'll take more of this in the next session. So let me begin with the concepts where I've written the statement again, which is limit f of x is equal to L where x approaches a. Now the next statement tells you how to read it, right? So Amy, can you read the next statement, what I have written here? How to read this particular thing?
The limit of f of x as x approaches a is L.
Yeah, so read this. Read as the limit of f of x as x approaches a is L. Perfectly fine. That is how it should be read. Now, will I actually dissect this statement to really understand the concept? So I've written 4 or 5 statements here. The first one is, a limit is the value that a function approaches as x approaches a specific value. In our example, specific value is a. We're trying to approach a. Now, how close can you go? That is the next statement. When we say x approaches a, and we read it as x approaches a, that means x get closer and closer to the number a from either side, from both the sides, but it is not equal to a. And that is important to understand. Sin x over x is not defined at x equals to 0, but you cannot always approach as close as, right? And find the value. What value are you approaching? If you approach a real value, then the limit exists. Otherwise, the limit does not exist. Do you get the idea, right?
Yeah.
From definition, now, once again, the definition was given to you earlier. From definition, the limit of a function may exist even if function is not defined at x equals to a, correct?
Mhm.
Provided the value of the function approaches L, a real number, from both the sides. So in sin x over x, it was approaching 1. For x approaching 0, so it has a limit, which is 1. The last statement here is, a limit is the value that a function approaches without necessarily being equal to that value, right? So that's a clause which I've added to our definition. A limit is the value that a function approaches without necessarily being equal to as x approaches a specific value. Now, there is a catch in this. That is to say, let us say we are talking about polynomials which are absolutely continuous. And if I say, what is the limit of the function when x approaches 1? Well, since it is continuous, you can approach at 1, no problems, right? So why not just substitute 1 and find the answer? Why to do a calculation with 0.0001 and so on? Does it make sense to you?
Yes.
So for a continuous function, we just substitute the value directly. So now it becomes more significant for us to understand this particular statement without necessarily being equal to, but it could be equal to. It could be equal to. When we say x is not equal to, that is to cover for the cases where it is not defined at a. So you may not be at a, but if you can be there, why not? That is the concept. So if you can be there, just be there and find the value of the function. If the value of the function is same as the limit, the function is continuous. So for a continuous function, substitute the value. Perfect? Now, let me remind you of what we did in our very first lesson. We actually began with finding the value of E, right? We said that E is actually given by limit of 1 plus x to the power of 1 over x when x approaches 0, right? Now, 1 over x is not defined. It is infinitely large. So 1 plus x to the power of 1 over x is not defined. Even if I put x equals to 0, you get an expression which is 1 to the power of infinity. That is also indeterminate form. So you have seen many indeterminate forms. You have also seen how to evaluate even such indeterminate forms. So we had a clear-cut approach. We approached from the left side, right? So we said, let's approach point minus 0.001, and we went and got this value of 2.7184. From the right-hand side, we again got the same value. We say that the limit of the function E is 2.7184. So that is the value of E, correct to 4 decimal places. So you remember the connection between what we already know and what we are going to learn. So I kind of introduced you to this particular concept right in the very beginning. And that's what we are going to do. Here again, I've introduced to a big concept of taking examples with exponential function E and now trigonometric function sine x. Now sine x over x is a key function to get into the trigonometry, which involves trigonometric functions, rather calculus, which involves trigonometric functions. It is very important to understand that the limit of sine x over x when x approaches 0 from the left side or from the right side, which we write like this. You notice this? X approaches 0 with a negative sign means approaching from the left side. When we say X approaches 0 from the right side, we write like X approaches 0 with a plus sign. That means from the right hand side. Now what I did was I just calculated the values. And when I calculated the values, I got 0.99999, which is close to 1. And we can conclude from both the sides, the value of sine x over x being approached is 1 as x approaches 0. Therefore, the limit of this function, sine x over x, which is indeterminate function for x equals to 0, has a limit, and the limit is 1. Perfect? Is that all clear to you?
Yes.
Both of you, because I'm trying to go a bit fast. I don't really like to do that, but still. But if you are coping up with me, then it's good. Najib, are you with us?
Yes.
Okay, great. So now, on the left-hand side, I've again given you the caption which says limit f of x equals to L when x approaches a. Limit of a function exists at a if and only if the value of the function approaches a real value when x approaches arbitrarily close to a from both the sides, right? Now we have two questions for you. The first question says, why limit of 1 over x when x approaches 0 does not exist? Can you answer this question, any one of you?
Is it because the limit from the right side and the left side, as you approach, they're not equal?
What are they equal to? From the left side, it is minus infinity. From the right side, it is plus infinity. Infinity is not a real number. So they're approaching a number which is not real, so it does not exist. And they're also approaching different infinities, right? Plus and minus. How about question number 2? Find the limit when for the function x minus 1 over x squared minus 1 when x approaches 0. Does this limit exist? Tell me.
Yes.
Yes. What is the limit?
Minus infinity plus infinity, I think.
No. Minus infinity plus infinity are not the real numbers. So when you do x squared minus 1, factor it out. You get x minus 1 times x plus 1. X minus 1 cancel. That means you have a whole at x equals to 1. Correct? That is one thing.
Oh.
But if you clearly, I mean, I'm going beyond, but you have a hole there and you will have a limit at that point. But let's look at the question clearly once again. It's a very common mistake. We are saying limit when x approaches 0 and the function is x minus 1, x squared minus 1. At 0, the function is continuous. If I put 0 there, I get 0 minus 1, 0 minus 1. Minus 1 divided by minus 1 is just 1. So what do I get? 1. So this limit exists, and the answer is 1. You see that? So in examination, one of the most simplest question, you may go wrong. If you don't read carefully, what is it written? Limit x approaches what value? So you have to pay attention to that, okay? Next question, evaluate limits. Now it is the real chance for you to evaluate. You can actually work with calculators if you want to. However, I have taken very simple values. We'll just work with ones and zeros so that calculator is not required, okay? The very first question is, find the limit of x squared plus 2x minus 1 when x approaches 1. Can you tell me the answer?
Would we factorize? So
Straight away substitute the value. So if there is a polynomial, you don't have to do much. In polynomial, you can approach and you can be there. It is a continuous function. Substitute 1. So you get 1 plus 2 minus 1. The answer is 2. Does it make sense? That's it. B. Limit when x approaches 1 for pi plus 1. What is the answer?
5 plus 1?
Pi. Pi is the number, right?
Yeah.
Irrational number pi. What is the answer? Pi plus 1 is the correct answer, Najib. That's what you said. The C is 1 over x when x approaches minus 1. The answer is?
1.
minus 1.
minus 1. And the next one is x approaches 0, x minus 1 over x squared plus 1. We already did this, right? Minus 1. The next one is limit x approaches minus 1 clearly, and the function is 1 over x plus 1. What is the answer?
Minus 1.
How about you, Amy?
Does not exist.
Why?
Because if you sub in minus 1, it's 1 over 0.
Perfect. Next
And,
one.
oh,
Yeah. Absolute value of x plus 1 over x plus 1 when x approaches minus 1. Now what is the limit?
Not exist, I think.
Does not exist because there is a jump discontinuity. So when we are approaching from the left side, the value is -1. When we are approaching from the right side, the value is +1. So both values are not matching. Since the values are different, the limit does not exist. Does it make sense to you? So a simple exercise to just take a review of what we did. So what you understood here is that direct substitution can be done for continuous functions, and don't lose that liberty of using substitution directly if possible. Perfect. Now let's move on and take the next part, which is limits from a graph. Now we are given a graph. You can see the filled in holes, those the values exist. The holes which are not filled in, they are the holes. The circles which are not filled in, right? Now looking at this graph, you have to answer all these questions. Beginning with A, limit of f of x when x approaches -4. What is the answer?
2.
Perfect. When x approaches -2.
2. No.
When x approaches 0, correct.
Oh.
When x approaches 0.
-2.
Correct. When x approaches 2.
2.
Does not exist. Because when you approach from the left side, you're approaching the hole. From the right side, you're approaching the filled in circle. The values are 2 and 4. They don't match. And therefore, does not exist. Perfect? Now at 4, what is the answer? It is a continuous function. So the value of 2 at 5, the value is 0. Now, it is important to also read the values of the function. So what is f of -4 from your graph?
F of -4. 2.
F of -2.
Oh, it's a hole, so.
Does not exist, right?
Yeah.
F of 2. So you can read the graph. F of 2 is the value 4, right? Now what you notice here is if the limit of the function and the value of the function is same, then the function is continuous. Do you understand? So if you make this table and work out, you will see that if the value of the function and the limit of the function is same, then the function is continuous. So for a function to be continuous, first condition is that limit should exist. Second is that the value of the limit should be value of the function. Is that clear to you?
Yeah.
Perfect. Now we'll talk about one-side limits. Now in this particular graph and the question which is related to the graph, you will notice that I'm asking you, what is the limit when x approaches -4 from the left side? That minus thing on the top of it, the superscript, tells you approaching from the left side. So whenever you want to find the limit at a point, you have to see from both the sides. However, sometimes we are only interested in finding limits from one side. For example, in a semicircle, you can go from inside out, but you cannot come from outside in since the domain is restricted, correct? So one side limits may exist. So that is why it is critical. So we'll just quickly go through some of them. A, what is the limit of this function when we are approaching -4 from the left side? So this is the left side. When we approach, what is the limit?
-1.
Correct. So if I take up this question, approaching -2, approaching 2 from minus side means this is your minus side and you're approaching this point. What is your answer?
0.
Correct. So easy to know, right? So that is how you could be answering such questions very easy to understand. Now, a good point to remember here is that limit exists at a removable hole. Now, what does it mean? All these holes, which are kind of connected, if I plug them, they can become continuous. Do you see this?
Oh,
So they are called removable holes. I could define another function and fill them up. However, we have a hole here which cannot be filled. This, because there is a jump discontinuity. So when there is a jump discontinuity, the function is discontinuous. Is that clear?
yeah. Wait, so you can't fill in holes at a jump discontinuity?
No, you cannot. If you try to, it is no more a function. It is no more a function, correct?
Yeah.
You cannot have two values at the same point. Now we are talking about piecewise functions. Piecewise functions are a very important part of calculus. Most of the time, we split the functions into many parts and then analyze. So we should be in a position to understand what a piecewise function is. So basically what we do is, as I've shown here, we have taken a function f of x, and we are saying that this function f of x is equal to x when x is less than -1. So it's a straight line with a positive slope as shown here. The second part of the piece is, it is x squared, a parabola opening downwards when the values are between -1 and 2. So this is this blue part which is shown, and the filled in circle indicates these values which are included. And the third part is a constant function which always will be a straight line. And since it is greater than 2, we have a circle which is not filled in. To answer the limit-based question, if you could first sketch the graph, looking at the graph, it is very easy to answer. That is one part. And looking at the graph, you could also write down the answer for such questions. Where is the function continuous and where is the function not continuous? Clearly, if the ends of the two pieces match, they are continuous. And if they don't match, as in this case, they are not continuous. Is that clear to you? So simple. Perfect? So to figure out whether it is continuous or not, you can, for this particular function, algebraically calculate what is the value of the function for -1, right? So if you plug in -1 in both the parts which are coming from left and right, you will get the limit, right? Basically, you'll find the limit from both the sides. If they match, then there could be a hole. So you have to plug in the value. See, what is the value of the function? If it is exactly same as the limit, then the function is continuous. So that is the principle. Now, based on this, we have a question for you. Question number 3. And this is the last question for the video. We have actually reached the end of whatever I wanted to teach you. So, Amy, can you read the question for me?
Find the value of the constant k for f of x to be continuous for all real numbers. Given f of x equals x plus k, x being less than 2, and kx squared, x being more than or equal to 2.
Perfect. Explain me, how will you answer this question? Najib, can you help me answering this question?
This is equal, I think.
No, k value could be anything. K could be 1, 2, 3, 4. So not for all k's. There is only one value of k for which the function will be continuous. Otherwise, it is going to be discontinuous. So
-2 plus 2, I don't know.
now don't give me the answer. Give me the method. We'll calculate the answer. So the idea here is that k plus x is a continuous function, a straight line. Kx squared is also a continuous function, a parabola. They could be discontinuous at x equals to 2. Since at x equals to 2, we have two different functions. One on the left side is a linear function. On the right side is a parabola, quadratic function. So what we will do here is substitute the value 2 for x. So on the left side, we get 2 plus k. On the right side, we get k times 2 square, which is 4k. We will equate both of them and find the value of k. You get the value of k for them being continuous, since for that value of k at 2, both the pieces match up. Does it make sense to you? So
Yeah.
simple as that. And here is a quick solution for the same, which brings us to the end of the video. So it is 11:56. We just have 4 minutes to go. So I'd like you to go through this particular solution where we are saying that we're basically equating limit of the function when we are approaching from the left side and when we are approaching from the right side. From the left side, it is a linear function. Plug in 2, you get 2 plus k. From the right side, it should be plus here, right? So it should be plus here, right? Okay. From the right side, it is 4k. Equate 4k to 2 plus k, and you get your answer, k equals to 2 over 3. So for a value of k equals to 2 over 3, the function is continuous. And this is your straight line, and that is the parabola, and that's the point which you will get common only if k is 2 over 3. Perfect? Does make sense?
Yeah.
That is all about limits, and I hope you have understood it all. You're definitely in a position to actually do questions from your notebook. Since you don't have any, I have got hundreds of videos. You could actually check some of these videos and then consolidate on whatever we have learned today. Does it make sense?
Yes, sir. Thank you.
Perfect. So we began with this particular concept of limits. We actually started with a very difficult function, which is sine x over x. It is not only difficult, but it is very important function. Half of the calculus is done with this particular function, and actually rest half will be done with e. So basically we covered up 2 different functions, their values, and we solved those functions with limit x approaching 0. And we also learned how to interpret whether a graph of a function is continuous or not. We also saw that the function could be discontinuous if the limits are not same from both the ends. Emmy, will you like to summarize what we have learned today in this session?
So the limit f of x, so as x approaches, let's say a, it should be like a fixed value.
Yes.
So L. And as x gets closer and closer to a, it should be from either side. And we said that x is not equal to a, however, it can be. So without necessarily being equal to it.
Yeah, without necessarily being equal to, but if it is a continuous function, you can substitute. Perfect.
Yeah.
Okay, continue.
And then you can do direct substitution. It can be done for continuous functions.
Yes.
And the limit exists at, so this was a new term for me, removable hole. So
yes.
You said that it can be filled, but if there are 2 holes, then it cannot be, if there's a jump discontinuity.
Yes.
And yeah, I think that was it.
Yeah. And the discontinuity could also be of infinite kind, 1 over x, which we came up with. So when x was approaching 0 from the left side, we were approaching negative infinity. And when x was approaching from the right side, we were approaching positive infinity. So the discontinuity could be of a couple of types. One, as we saw just now, infinite discontinuity. The other one is removable hole, which can be filled in, and the jump discontinuity, which will remain as a discontinuity. To figure out which kind of discontinuity it is, we can find the limit and then get the answer. If the limit exists, in that case, we will definitely have a whole type of infinite, because you're approaching from both the sides, but you're not quite there. So there is a discontinuity, but you have a limit. That means it is a hole, which could be filled in. If you have jump discontinuity, then from both the sides, you're going to approach a different value. Limit will not exist. But if there is no discontinuity, then the value of the function and the limit will match. And so the function is continuous. Perfect. That is how we are going to do it. So now I'll recommend you to go through some of my videos and then take them as your test question. I'll also send you over a few videos which could be treated as your test on this particular topic. Tomorrow, we are going to take up indeterminate functions and learn techniques to solve all those functions. Those techniques are going to help you as we move along in calculus. So after 2 lectures, we'll actually begin with derivatives. I hope you find it interesting and useful. So Najib and Emmy, thanks a lot for joining me. Feel free to write your comments, share your views, whatever questions you come across, just post them over to me. You can send your solutions for checking on WhatsApp as we have been doing. So we are actually totally connected and I'm here to help you out. So feel free to, ask for whatever you want to, right? The idea is that excel and achieve your objectives and goals, right? With that, thank you again.
Thank you very
All
much.
the best.
Thank you so much, sir.
Thank you.
Thank you. Thank you.
Bye.